All right, and bang on time, it's 9 o'clock, and this is day 3 of GSE UK virtual conference. And I'm pleased to introduce the DB2 stream today. The first session up, we've got Julia Carter from Broadcom, who's going to explain all about Explain. So this is a session that's been has gone down well at iDoug last year, and looking forward to it because there's always things you don't realize that you didn't know. So take notes, enjoy, and please do the feedback at the end. So over to you, Julia.
Great, thank you, and good morning, everybody. Thanks for joining bright and early. I assumed, having been a DB2 DBA for quite a few years, that I should know a thing or two about explains, as I used to run them probably every day at one point in my time. But it turns out that I didn't really know as much as I thought I knew about the overall concept. So this session aims to break things down a bit and start at the beginning and try to take a look at the complete picture, but without getting too technical on any particular part. It is most definitely a beginner session, so I won't be offended if some of you very experienced people decide to drop off or mute me. Anyway, let's get on with it. I'm just going to stop my video in case I have any issues with bandwidth this morning. Okay, this is our agenda. I'm going to start with a very quick look to show where this topic fits into the bigger picture of DB2 performance. Then we'll move on to look at the functionality of the DB2 optimizer from a high level. And from there, we'll talk about execution plans or access paths, which leads us finally to explain what it is, how we can run it, and some suggestions for interpreting the results at a very basic level. We'll also have a quick look at the different ways this data can be displayed either directly in the DB2 catalog tables or visually with a tool. And at the end, if we have time, we'll have a very quick look at some best practices. And please feel free to interrupt me at any point with questions. I probably won't be keeping an eye on the chat window, so somebody shout out if a question comes up in that, and hopefully somebody here will know the answer, maybe not me. Okay. There are various components which contribute to the overall performance, like the application running on DB2, the DB2 subsystem or the data sharing group, and the operating system, ZOS. And the explain or access path topic fits in both the application and DB2 subsystem spaces because it's related to SQL and some of the configurations in our subsystems. Most performance issues are probably related to the application itself rather than being system related. And there are these 3 main aspects to consider. We've got the physical database design, things like normalization, indexing, partitioning, size of the objects or volume of data in them, referential integrity, and statistics, which is a really key part. The second is the way the SQL is written. Does it have indexable predicates, or is it using stage 2? What are the joins like? And then finally, we've got the application design, which is things like the use of cursors, dynamic or static SQL, if there's host variables, and the commit frequency. And all 3 of these areas can have a potential impact on an access path. Therefore, what we see when we explain an SQL can vary depending on how these things have been set up or defined. So now we'll start to look at the optimizer. And this is my really simplistic view of the optimizer and how it works. Hang on, yeah, it flashes. We'll talk about some of these aspects in more detail over the next few slides, but here's just a summary of what's going on. We have some key inputs like our SQL statement, which hopefully has at least 1 predicate, usually a where clause. It might have literal values or host variables. it might be written by an expert programmer who knows certain rules that they should follow to give DB2 the best chance at good performance. Or it could be written by a back office person who doesn't know so much about writing efficient SQL, or anybody in between. And as users, we don't really want to worry about exactly how DB2 is going to get the data back that we're looking for. That's the job of the optimizer, which I've represented here with this funky light up brain thingy. And through our SQL or DML, we're providing the what. That's to say, we write SQL to retrieve data based on our business requirements, be that for a report or a transaction or a batch process. It could be a simple select that we issue ourselves, or it could be a really complex piece of SQL that's in a package or a program. It may have even been generated by our application based on screen input. It doesn't really matter what it is, simply that it defines what we want. And then moving around to the top, we've got tables and indexes, or table spaces and index spaces to be precise. This is where the data is actually stored. And this part also encompasses our general database design and our subsystem configuration, but I couldn't really find a decent picture for that. Then next round, we've got catalog statistics. And these do have a significant impact on what the optimizer can know about our objects and their data, and therefore is what it uses to calculate different possibilities to access the data. And talking about stats, during my research for this session, I read an article by Robert Catchwell of IBM, excuse me. And in his article, he mentioned that 75% of query performance issues that IBM support Ascent are resolved by fixing the stats for the object involved, not by having to rewrite the query or adding more indexes, but by improving the stats available to the optimizer. So I just wanted to make that point, that catalog statistics are important. Then over on the right, we've got the fudges. I didn't know how else to represent these pictorially, and it's always nice to see a bar of fudge even at 9 o'clock in the morning. But these represent the methods that we can use to manipulate how the optimizer sees things. And finally, at the bottom, the little picture of a maze, this represents the access path. The optimizer will calculate various possible access paths, and then it goes with what it calculates to be the cheapest. So the optimizer is a subcomponent of the database services address space, or DBM1. It makes cost-based decisions. It will calculate multiple possible access paths and then select and store the cheapest. The cost is essentially determined by the number of rows that get passed from one step to the next within the query execution. And this can be seen in the CPU and IO costs. The optimizer can do some clever things. It can transform some predicates to make them more efficient, but it can't fix absolutely everything. We still need to do our best to provide DB2 with some half-decent SQL. You've probably experienced for yourselves and pulled your hair out over SQL that's been generated by tools or an application, or has been optimized maybe for a different RDBMS. And in those cases, DB2 might be able to transform or rewrite and therefore improve some of the predicates based on its own internal rules. And there's an awful lot of concepts that query rewrite covers, including subqueries, casting data types, nested table expressions, and way more things. There's also transitive closure, which I've got the basic example of here, which means if we have a predicate where A equals B and another predicate where B equals C, then the optimizer concludes that A must also equal C. which helps it a lot when DB2 is bringing together data from different tables, as it can propagate local predicates across tables, helping to give more options for indexes, stronger filtering, and more efficient table access. If you're really interested, you can view the rewritten queries and see the before and after SQL text. If you've got a tool that can show you, then it's very straightforward. But if you need to run the query yourself against catalog tables that contain the data, it will probably need to be some fairly fancy stuff because it's held in XML. So it's a bit awkward to read. And the last point here is query parallelism. This allows for DB2 to break down a query into multiple pieces to execute it in parallel. And then it merges the individual result sets back together and return them to the process that's executing the query. But we'll need to weigh up parallelism. For transactions, it's not really recommended from a performance perspective, as the extra overhead that's required for establishing and coordinating the parallel tasks is likely to exceed the normal or expected response times for a query that processes very little. But on the other hand, parallelism could help a lot, and it could help with cost reduction in batch processes, as a parallel task can be offloaded to zip engines if there's capacity, obviously. So parallelism is probably better for large data warehouse type queries or batch processes. And enabling parallelism can be done at a subsystem level via ZPalms or at an application level. The optimizer's calculations are based on our subsystem configuration, the statistical data that it has available, and our database design. For system configuration, this encompasses things like ZPalms, which can impact query parallelism, as I've just mentioned on the last slide. Without accurate statistics, DB2 can't precisely estimate, oh wait, that doesn't make much sense. It can't really estimate the cardinality and distribution of data which can impact the decisions that the optimizer makes. But DB2 only really needs detailed distribution statistics if we have problematic SQL, which extra stats can then help with. So we need to be sure that we provide the optimizer with the correct level of stats, which is usually just basic stats, in order to help make its decisions. An important part of the calculations are to do with the filter factor of a predicate. This is a number between 0 and 1, and it's an estimate of the number of rows in a table for which the predicate is true. So they then qualify for that particular predicate. And a very simple example, which I've read in the DB2 manual, would be something like, if there's 100 rows in a table and there are 5 distinct values, A, B, C, D, and E, then DB2 assumes that 1/5 of the rows are an A, 1/5 of the rows are a B, and so on. So 20 of the rows for each value means 20 divided by 100 gives us a filter factor of 0.2. The last point here, it doesn't know what it doesn't know. What I mean by this is that in the case of host variables or parameter markers, the optimizer can't know what the value is until the value is actually passed to it. And similarly, it may be having to work with objects that have insufficient statistics or out of date run stats, which don't reflect how the data is anymore. So it can only work with what it has available to it. I guess that's pretty obvious. And finally, talking about the optimizer, it's invoked at bind time for static SQL or at runtime for dynamic SQL. And what it does is it parses and syntax checks the SQL to ensure valid SQL is being input. And then it will analyze all of the environmental data it can get its hands on and start calculating possible execution paths or access paths to actually get the data. At this point, it may need to rewrite parts of the SQL to make them more efficient. Then it needs to create the computer readable instructions that are required in order to execute the now optimized SQL, and things like which indexes it will use, how many, how it will join any tables that are in there. And spoiler alert, it might not be how you've coded it. So it might transform some of those joins. It will also look at intermediate tables that it might need to do sorting of data and so on. And finally, it stores the instructions, and we'll have a look at these different possible targets a little bit later, I think. Okay, so finally, what is an access path? I've taken this quote from the DB213 manual, but I'm pretty sure it's in all of the manuals for the last few years or even decades. And it says, the access paths that DB2 uses to process SQL statements are among the most important aspects of query performance. Okay, so we know that these access paths are important, but why? Well, there are often several ways to implement a piece of SQL, and these are the access paths. And although the end result will be the same set of data being returned, regardless of the access path used, the performance between the different access paths is likely to vary. DB2 does all sorts of calculations to choose which access path will be best. And the access path defines how DB2 will access the data to satisfy the SQL. They specify which tables and indexes will be used, plus any immediate tables for sorting data, and the access methods that will be used in order, and the order that DB2 will access the objects. So that all sounds quite straightforward. But then what makes a good access path? Well, it wouldn't be a DB2 session if we didn't say it depends at least once, but I think I'll only say it once. And of course, a good access path does depend on a lot of things. Depending on the type of activity, we would expect to see different types of access paths. So for example, the difference between online transactions at one end of the scale and batch processes at the other end of the scale, and ad hoc queries, which might fall somewhere in the middle. We probably don't want to see table space scans for online transactions, but maybe for batch processes, it's more efficient to do that. And sometimes with ad hoc queries, we compromise on not having a perfect access path because the cost of improving the query or the access path may be far more than the cost of the CPU to just run it. And if it's a one-off, maybe that's okay. As we know, the optimizer can do amazing things, and it can rewrite and reorder some predicates, but there is still good standards that we should follow, which can help to get us a better access path. Things like only asking for rows and columns that are actually required. I'll be talking more about predicates a bit later, but where possible, use stage 1 index matching predicates and use leading columns from the indexes to help matching index access. Equals predicates are the best, but it's often not possible to use equals or in your SQL. So it's important to understand how the different operators affect access paths. I might have mentioned this once or twice. Accurate and appropriate stats are really, really important. Appropriate use of indexes, after ensuring uniqueness, if that's necessary, then indexes should be there to help improve query performance. However, there's an overhead to having indexes as they need to be kept up to date when data is changed or added. And one particular catalog change that comes with DB213, which Håkan mentioned at IDUG, is that they finally got rid of an index which has been redundant since DB2 version 6. And the same sort of thing might be true in our applications. There might be indexes which were useful at some point, but things have moved on. We can potentially drop them and save the overheads from having to update the index with DML and utility processes. Easier said than done in many cases in the real world. I do vaguely recall that making DBA-driven changes could be a real challenge. So yeah, easier said than done in some cases. But anyway, DB2 works out access paths based on filtering out as much data as early as possible. Good programmers should be considering this as part of their job. There are several ways that SQL can be written probably, and they'll achieve the same results, but some methods are likely to be better. So it's important that SQL is written and tested with that in mind, with performance in mind. Join methods and order are particularly important. If you have to join 5 tables, then you want to try and join them in an order which filters out the most rows earlier. So fewer rows are then passed to the subsequent steps. And the final section here is host variables or parameter markers versus literals. Using variables is generally a good technique for both dynamic and static SQL, as it fosters statement reuse, either in terms of a package for static SQL or using the dynamic statement cache for dynamic SQL. This can save CPU by not needing to do a full prepare every single time. However, it means that when DB2 chooses the access path, it doesn't know the actual values that might be passed. So could be using default filter factors, which is where it assumes the uniform distribution. But skewed data can be a problem. And in the previous example, where I said that a column has the values A, B, C, D, and E, each with 20 rows in the 100-row table, in reality, if A actually has 96 instances and the other letters just have 1 each, this is skewed data. And the access path might then not be very optimal. So that's something to bear in mind. This slide covers the various ways that you can preserve an existing good access path, and other times when we need to revert back to the previous access path due to a performance regression, or reset or wipe out an access path completely. The explain only bind parameter will insert the latest would-be explain information into the explain tables. So you can analyze what would happen if you were to bind or rebind right now. A bind with explain only doesn't insert a row into syspackage or insert or update anything into the directory, but it does acquire the same locks and uses the same resources as an actual bind would use. So just something else to bear in mind. If you need to analyze whether an access path is likely to change, you can use bind parameters AP compare with error, and on bind or rebind, if the access path is structurally different to the current access path, then the package will not be bound or rebound. You also have the warn option, so AP compare warn, if you want to know if there's a difference, but you're happy for the bind or the rebind to happen anyway. And I should just point out that the AP in AP compare and AP reuse, which is coming up next, that stands for access path. So AP reuse with the error option means that DB2 will attempt to reuse a previous access path that it has stored. And if it can't, then it doesn't do the bind. If it can do the reuse of the access path, then it will. If you can, it's great to rebind without AP reuse, because there have obviously been changes and enhancements in the optimizer over recent releases, which could significantly improve things. And as long as the package isn't invalid and you have plan management enabled, then you can always switch back to the previous access path if needed. AP reuse provides a safety mechanism for minimizing the risk of an access path regression. But at the same time, you could be missing out on progression or an improvement, which could result in cost or time saving. As I've just alluded to, if you need to back out an access path, usually due to performance regressions, then as long as you're using plan management, you can switch to the previous or original version of the package with a straightforward rebind with these keywords, switch, previous or original. The package must be valid, otherwise the switch doesn't work, unfortunately. Have I mentioned stats yet? I'm not sure, but stale stats can be a real problem and can impact access paths. And the cleanup of stale stats is particularly important from DB212 because of the automated profile-based stats collections. So these now stale stats could be specialized stats from a one-off tuning exercise and could be completely irrelevant to our current situation. So there's a few ways to fix this. You could use SQL to identify the stale stats and then delete them. And there's examples of that in the manual. You could update or create statistics profiles to remove any keywords that are related to the unneeded stats, and then run stats or reorg or load with use profile. And that will collect the new stats and delete stats that are no longer included in the profile. The third option is to run stats with reset access path. And if you do that, it doesn't collect any statistics in the run stats, but it does reset the values of certain columns in certain catalog tables, and it will delete rows from others. This also invalidates the dynamic statement cache, but it doesn't affect real-time statistics. But when it resets things in this way, it sets values back to -1 in lots of cases. It will set the clustered indicator in sysindexes back to n, and other columns will be blank, or they'll take the timestamp of the reset. So with all that in mind, you need to be really, really sure that you want to do this. It's like a factory reset of the stats for the object or objects that you're runstatting. After the reset, you would then collect standard statistics for those objects. So here we are after, crikey, 34 minutes. We've got to the DB2 explain bit. I've got a quote here from the Broadcom Performance Handbook, which I think sums up what DB2 explain is quite nicely. The DB2 explain facility is a means for estimating SQL execution cost and for externalizing the transformed, rewritten query and selected access path. It is one of two key techniques, with the other being benchmark tests for predicting the performance of production queries and applications. Explain should be a part of every SQL development and testing process. And here's a bit more about it. There's a set of 20-ish explain tables, which includes the infamous plan table. And these explain tables contain information about SQL statements and functions that run against DB2. Each row in an explain table describes some aspect or a step in the execution of a query or subquery in an explainable statement. So this is the access path information, and for every statement, you'll see at least one row, sometimes a couple, and sometimes many rows, which represent every broken down element of the statement. The values in these rows identify all sorts of things, including the query or the subquery text, the tables and the other objects involved, the methods used to carry out each step, the cost information about those methods. There's a lot of information there. And the data stored in these tables can help us with our ongoing database design, to help us to know when is best to rebind packages or programs. And from a performance perspective, the data helps us to understand the access path that DB2 chooses. And the last point here is that the primary use of all this explained data is to investigate the access path of the select parts of the statement, but you can run and explain against all sorts of SQL. There are various ways to generate and explain of an SQL statement or group of SQL statements. I'm going to show some of these later, so I won't go into the detail now. You need to have the plan table and explain tables created with an owner of SQL ID for dynamic SQL and the plan owner or the package owner for static SQL. And these explain tables, you need to understand what they are and what their columns and codes are in order to begin interpreting the access path. A quick point here is that you can grant explain to an authorization ID or a role or to public. It's a system privilege, and it allows the user to do an explain without requiring the privileges that are needed to actually execute the statement. And the with grant option lets that person then, or that auth ID then, grant the explain privilege onto somebody else. So how to get started with DB2 explain? You might well need the full set of explain tables, or at least quite a few of them, to be able to use a visual explain tool or another expert tool. But if you're doing your explain in Spoofy or just via DSN Type 2 or something like that, if certain tables don't exist, you simply won't have that data. But the explain will still work as long as you have the plan table. You can create the full set of tables by using the DDL that's in sample job DSN TSC, or by using the store procedure, admin explain mate, or as I normally do, I just generate the DDL from system maintained set of tables. I amend it to use my user ID as the owner, and I create it in one of my own databases. In your subsystems, you'll likely see multiple instances of explain tables. Probably a lot will be for individual users, other DBAs, or the developers maybe, but there will also be the system maintained tables, and probably some sets of tables related to SQL optimization tools. And just while we're talking about these tables, when you migrate from DB2 12 to 13, it is recommended that you convert your DB2 12 explain tables to DB2 13 during or soon after your migration. You can use the same store proc admin explain mate, but you would use the standardize action instead of one of the create actions. Here we're looking at one way that we can invoke and generate the explain information. This is doing a rebind of a package with explain yes specified. Beware that the default for the explain attribute is no. So for new packages, you need to make sure that you have that to set if you want to be explaining them. Doing the bind or rebind re-optimizes the SQL. It creates a new package, and with explain yes, it populates the explain tables, except for DSN query table and DSN statement cache table. And now look at another way to invoke explain using explain all or explain plan. And my example is done in Spoofy, which I find the easiest. The first statement, explain all set query no equal 1, 2, 3, 4. That's a syntax which invokes explain and populates the DB2 tables. Because I'm running this under my own ID, it's my personal set of the explain tables that gets populated. Normally for packages, that's the application uses that the rows will exist in explain tables associated with the package owner. And just a note here, explain all and explain plan are the same. The result is the same. I guess it's historical that we have two ways of doing it, but it means the same. And then after the explain all statement, now looking in this orange box, we have the SQL statement that we want to be explained. And then we have a query to extract the data back out of the plan table for query number 1, 2, 3. And finally, select from the DSN statement table, again, for query 1, 2, 3. So now we'll go on and have a look at the output from that. So on the previous screen, it was the Spoofy input. I just mentioned the 2 select statements, and here are the output. And first we start with the plan table. I select some specific columns that I'm interested in, and then I select everything with this pt.*. And that's just so that I've got all of the columns there if I need them, but the ones that I'm sure I'm going to be looking at, I have at the beginning. And on the previous slide, we saw that In the explain all statement, I set query number to 123, and this is what I now have as my main predicate when querying the explain tables. Query number links all of the tables together to make it really easy for you to query them. We have the start of the explain output from here. This is from the plan table, and after query number, we have the join method, the table in question for this part of the statement, and we can see the access type, and this gives us a good indication of how the optimizer will access the table. And then we've got the name of the index that's going to be used for access, and as is the case here, we've got match cols, which will give us the number of index columns that are used in the index scan. We also have a couple of columns displayed here for the prefetch, the join type, and whether the results can be achieved using the index only. In my simple example here, there's no prefetch or joins, and the table data will need to be used. One thing about the plan table is that as it's been added to over the releases of DB2, the columns are no longer really logically grouped. So you may feel the need to manipulate the order of the columns to be more meaningful, as I've done here. There are many more aspects of the explain output and a really chunky section of the performance guide explaining every column and every option and what the values really mean. I'm only going to highlight a few of them over the next couple of slides. But while we're still here, my second query against the DSN statement table, this shows us the estimated processor cost, both in milliseconds and service units for the query. And these can be really useful for looking at relative costs. So, for example, if you make an improvement and the cost reduced by half, that's an easy and useful mechanism for checking the expected cost or efficiency of the statement and whether you're going in the right direction with your changes. Another way to invoke explain is with a visual explain tool. There are a few out there, and this is a prototype of the Broadcom one, but you can see immediately how the SQL is clearer in this format with different parts of the syntax color coded. It's quite easy on the eye. Then, as you'd expect, there's a chart showing the access path, and for lots of people this is much easier to read and interpret more quickly than looking at the data in the explain tables, as it pulls a lot more information into the chart, and it's a very logical design. And these charts are normally read from left to right and bottom to top. And at the bottom here, we have the raw data from the plan table. And don't look too closely at the DAF query. I think I was very short on imagination and sense when I put this together. Another option for doing an explain is to use an expert tool, which does the explain for you, and it helps you to interpret the results and get insights and recommendations and potential places to improve. You can get various different reports out of these tools in different formats. It does some of the analysis for you, and based on rules and recommendations, this sort of tool can help you to improve your SQL. You could integrate something like this into an Endeavour or other source code management process to use cost filtering to detect access path changes or cost changes before it's too late, or to at least notify you if there's a change. You might use an expert tool to do a base explain, and you keep that baseline, and then subsequent explains are also saved, so they can easily be navigated between, and you can compare between them as time goes by. And other SQL performance tools also offer basic explain facilities. And this is just an example of the design rules in Plan Analyzer when looking at predicate analysis. It gives this easy to read explanation of rule number 82. So it just helps to speed up the analysis that you need to do and give some recommendations in English along the way. Interpreting access paths manually isn't something that you can learn in a 1-hour session or the 15 minutes that we've got left. Unfortunately, we could talk about everything in the plan table for an hour on its own. So I'm just going to highlight some useful things which you'll probably want to consider. But reading about all of the columns, their possible values and meanings, and seeing these things in action is really the only way to fully digest what's going on, why it's going on, and whether it's okay or not. When I'm reviewing a query, I tend to initially check the output from 3 tables in order to give me a better idea of what's going on. I often need to read the manual to remind me of what the different columns and values mean, but these are my 3 go-to tables that I always review. In the plan table, I normally check the table and access or index name and the access type, which tells us how DB2 is going to access the data. There are over 20 possible values for access type, but there's probably several that you'll see very regularly, and there might be some that you maybe never see because they're related to specific things that you might not use, like an accelerator or doc ID lists. And this essentially tells us if DB2 will use an index or scan a table to get the data that qualifies. Prefetch, the mechanism for reading a set of pages into the buffer pool in a single synchronous IO operation. Then we've got method, which tells us about the type of join between 2 or more tables, and if there's a sort. DSN statement table, which I mentioned a couple of slides ago. This gives us the estimated milliseconds and service units. And the last one, DSN filter table, this tells us the processing stage in which each predicate is processed. Various features of the access path have multiple columns related to them in the plan table, like for joins. I think I've got an example of that coming up. And there are lots of places to look. It might not just be in the plan table, it might be in other explained tables. So if you want to see where the predicate evaluation phase takes place, whether it's before or after a join, you'd find that in the DSN predicate table. I need to mention the predicate stages for completeness, so I'm going to go through this quite quickly. The DSN filter table specifies which stage a predicate is at. Stage 1 predicates are evaluated in the data manager component, and they are indexable where they can match index entries, or they can use an index for some screening or do some page range screening if only certain partitions are being accessed. Stage 2 predicates are where the predicate is applied on previously returned rows, so it's less efficient. And stage 3, this is not an official stage, but it's another way of filtering. And this is where the programmer codes the programs to bring the data back into the program and filter it there. You won't see this anywhere in the DSN filter table. It's as a possible stage. It's just something to be aware of. But this is not likely to be anywhere near as efficient as what DB2 can do. So just look out for that. Over the next couple of slides, we're going to have a look at an example of interpreting one aspect of access path. And in this case, it's match cols, which is the number of matching columns of index keys that are used in an index scan. So you'll only see this if the access type relates to index access. In this first scenario, we're selecting everything from the table, and we have equals predicates on the columns C1 through to C5. We have an index on column C1, C2, C3, and C4. So this gives us access type of I for index and match cols of 4. The predicate that's on C5 will be evaluated once the data has been retrieved. This query doesn't have a predicate on C2, the previous example did. So in this case, the index can still be used, but only matching for column C1, because column C2 is missing. We can take advantage of index screening for column C3 and C4, which helps by reducing the number of rows that qualify while searching the index. And again, predicate on C5 will be evaluated once that data is retrieved. The third example gets a gold star because the select statement now is only selecting the columns we're interested in. And we have predicates for the 4 columns in the index and nothing more. So we have an access type of I for index, matching columns of 4, and it's index only. So it's really efficient as there's no need to access the table's data pages as well as the index. I talked about filter factors earlier, and I think that we can probably all agree that a low filter factor is great, but we can probably also agree that a high number of matching columns is great, and a high value for match calls when only a single index is available to satisfy a query is really great. But if there are multiple indexes that the optimizer can choose from, it will need to weigh up which is actually the best, and it isn't necessarily the index with the highest matching columns. And in this example, the table EMP has two indexes, one on department, role, and location, and a second on EMP ID. There are predicates on department, role, and location. So for the first index, those predicates could give match calls of 3 and 20 rows might qualify. But in the query, there's an equals predicate on EMP ID. So although that would just be match calls of 1, only 1 row would qualify, meaning that index 2 is definitely the better option. It will examine the fewest entries and qualify the fewest rows. I mentioned that there's lots of different ways or different places to look at things about joins. Here's just some of them, but because I'm running out of time, I'm going to skip forward a bit more. The dynamic statement cache. The purpose of dynamic statement cache is to reduce the overheads associated with dynamic SQL compared with static SQL. The main overhead is determining the access path at prepare time, and this increases with each table in the SQL. And the first time that the SQL is executed, a full prepare is performed and the SQL is written to the dynamic statement cache. And each subsequent time, the same piece of SQL executes, assuming that a match is found in the cache, a short prepare is done and the SQL and access path are copied into that thread. We can view the SQL in the cache, and one way is using a performance monitoring tool. This panel shows the contents of the dynamic statement cache, and I select the first piece of SQL. We can see some high-level information about it on this screen, but there's more as we page down. All sorts of counters and clocks which help us to understand what's going on. My example is rather boring because our environments are often boring from a workload perspective. But at the bottom of this panel, we see the full SQL that is in the cache, and we have the option to explain it. So I do, and here's the output. First of all, we've got the details from the plan table. Then below the dashed line, it tells us a bit more about what's going on, including the estimated cost with some words to clarify what we're looking at. And in this case, we can see that the estimate of the cost is made without using default values. So that's good to know. And it tells us about the access method, the lock that will be acquired, and so on. Another way to view and explain the SQL that is in the dynamic statement cache is to issue the explain statement cache all statement, just like this. I've done it in Spoofy because it's quick and easy, but you can see that I ran before I ran the explain, I've counted the rows in the DESN statement cache table. Then I've counted them again afterwards, and we can see that 2,919 rows have been added to the table with the explain info for everything that was in the cache in the moment. And I can now go and browse that table if I like, do whatever analysis I need to do. And the last thing I'm going to mention on dynamic statement plan stability is where we can stabilize the access paths of dynamic SQL, which can be really useful. You need to set a ZPalm to enable this and then run this explain statement. But it's a cool feature from DB212. So I guess it's not new, but it's still cool. A few more options to consider if you need to do some fudging, time check. I'll go through some of these now. Reopt is another bind parameter which enables queries to be reoptimized at runtime. This means that the statement is reoptimized when the literal values for the predicates are known. The default or normal setting is none. And if you choose always, then as you might have guessed, the access path is then determined for every execution of the statement. The option once is applicable to dynamic statements, and it reoptimizes on just the first execution, and then that access path it persists until that statement is invalidated or it needs to be prepared again. For auto, you let DB2 decide if a new access path is needed or not. when considering always or auto, the benefit is that you have a customized access path, which is good when data is skewed, but on the downside, you have the overhead execution time. So another thing that needs weighing up. Traditional opt-ins have been around since DB2 version 6. They're often considered to be a last resort because they can be quite a challenge to create and to maintain. You need to set the ZPARM opt-ins to yes, create an additional index on the plan table, and then you insert your optimized access path rows into the plan table. You give the hint a name, and then you rebind the package to give it the hint, and you use explain yes to get the verification that the hint was actually used. And if it's dynamic SQL, you can use the set current optimization hint special register to point to the hint row that you want to use. But there are potential issues with traditional opt-ins. I'm not going to go through them now because I want to highlight a better way, but I think the general recommendation these days would be to avoid old style opt-ins if at all possible. I know that probably everybody has the odd opt-in knocking about, which you can't get rid of. So the new version is the access path repository, and this is the new way to influence access path selection. And I'm saying new in quotes because it was introduced back in DB210 and then further enhanced in DB211. So not exactly brand new, but still newish to some of us. But anyway, it gives us options for system level access path hints and optimization options. And there's a new, in quotes again, set of tables which are populated by the bind query command. And I'll come to that in just a minute. So looking at predicate selectivity overrides, DB2 can't always estimate the filter factor. So for certain types of predicates, like the ones I've listed here, it has to use default filter factors or inaccurate estimates. The default filter factors can be overridden with predicate selectivity overrides, and we'll now quickly look at the process for doing that. First of all, we capture the explain information and populate the DSM predicate table and the DSM predicate selectivity table with model rows. We then modify the contents of the DSM predicate selectivity table to contain the details of the override that we want. We then insert the rows into the DSM user query table, then issue the bind query thing with lookup no, which takes us it takes the input from every row in the DSM user query table and the related tables and populates the sysquery catalog tables with the access path overrides. And like with the standard explain tables that use query no or query number to link everything together, in this case, query ID is the column that correlates the rows in the sysquery tables. We then validate that the appropriate rows have been created by issuing the bind query lookup yes statement. And assuming that all is okay, we then delete the rows from the DSM user query table, so it's ready for the next thing that we need to add. And just to note that if the selectivity override can't be used, then DB2 inserts a value into the remarks column on the plan table, and the value contains a reason code that indicates why the selectivity override was not used. And there may be additional diagnostic information written in the remarks column for that row in the plan table. Okay, moving on now, stats feedback. This is worth looking at if you haven't already. When DB2 selects the access path for an SQL statement, it identifies missing or conflicting statistics values that might, if you collected them, improve an access path. DB2 holds this statistics feedback data in memory until an interval that you specify, and then it collects the data in the, or it stores the data in the sysibm.sysstat feedback catalog table. At DB211, that data was just there for us to use for analysis, or tools might use it for recommendations, and that was all good. However, from DB212, the stat feedback profile ZPARM has a default of Y, And that may have been creating a whole load of maybe hundreds or thousands of run stats profiles based on SQL being run, including the rubbish spoofy DSN-TEP2 type stuff that we accidentally on purpose run from time to time. So while having this feedback could be invaluable and help us to take the right stats to improve particular access paths, we might not want all of it. So something else to bear in mind. Another tool we have available to us is virtual indexes, which have been around since DB2 version 9. And this is a what if index. It's not physically built, but it uses stats from the catalog table, and it allows us to amend those stats. And we can hypothetically test different possible options, like creating a brand new index, changing the order of columns in an index, and so on. We can do an explain to see whether the optimizer would use the virtual index if it were to physically exist. And virtual indexes are often exploited by vendor performance tools, but you can create them yourself if you like. New explain tables must have the same owner as the plan table. So virtual indexes table has been around since DB2 9. Key targets has been around since DB2 11, but they need to have the same owner as the rest of your explain tables. So as I mentioned, vendor tools will often use virtual indexes, but you can experiment yourself as well with a little bit of caution, because an invalid index definition could be ignored by the optimizer, but you won't necessarily know it's invalid if you've inserted or updated the rows yourself. And here's an example of the SQL that could be used to insert your own virtual index definition into the DSN virtual indexes table. It's quite straightforward to set up, but I think most virtual indexes are probably created and managed via a tool. Okay, the last couple of slides and points now, looking at some best practices. Using SQL coding techniques to consolidate database calls is really quite critical to application performance. And this does require knowledge and some experience. If as DBAs and developers, we can familiarize ourselves with database features and test them out, then we can work out where we can make performance gains by using or maybe not using some of these features. The most efficient query is the one that's never executed, but obviously we have to execute some SQL, a lot of SQL, but we need to make it as efficient as possible by only calling the database when necessary, doing the work in the fewest number of calls, and coding the statement with performance in mind. We should try and prevent unnecessary sorts, and we can do this by simple things like removing order bys when the application doesn't care about a specific row order. Distinct obviously needs to be used carefully, and we should try to use union all instead of union when possible. Adding indexes needs a lot of analysis. They won't always be beneficial, and we have to consider the overhead for DML and utility operations. Stats. As I mentioned quite a few times, the optimizer decisions are based on the stats that are available to it. If we have to bind a package against an empty table, which will later contain a significant number of rows at runtime, then the access path will probably be completely wrong and very inefficient. We need to consider carefully when to rebind and which options we use for the rebind. And run stats is not free to run stats. We need to consider when to run them and with what scope. We have a lot of information available to help us with this now. And if possible, let your housekeeping be triggered by real-time statistics thresholds. Okay, that's about it from me. Thanks for being here. Sorry, it's taken me nearly the whole hour. Please provide feedback online or use a QR code, and thanks, and have a good rest of the day.
Thanks very much, Julia. There was so much in that. That was brilliant. And just to bear in mind, there's over 54 foils here. And if you think about each one taking sort of just a few minutes, 5 minutes, 10 minutes to perfect, you just realize how much time people do put in to their presentations. So thanks so much, Julia. And
thank you.
Yeah, it's really good. There's so much in there, as I said. I don't know whether there's any questions. There's a lot of well done and thank yous, so that's good.
I think I saw one just about the presentation. I think it's available from the agenda.
Yeah, I think after a couple of weeks, all the sessions should be available on video via Vimeo
Right.
for GSE members and people that registered. So that should all be uploaded after a couple of weeks. Gina
Okay.
has to do all the editing, so it takes a little bit of time just to sort everything out, but should be ready in a couple of weeks, I think.
Cool.
Okay,
Okay.
so
Well, 10 o'clock.
that's great. Time for a 30-minute break. Get a coffee, stretch your legs, relax for 30 minutes, and we'll be back in at 10:30 with Javier Estrada Benavides with Sharing is Caring in DB2, all about concurrency and sharing DB2 resources. So looking forward to that. That's at 10:30. And until then, have a good break. See you in a bit. Thank you.
Thanks all. Bye-bye.